Okay. And let me take a PowerPoint here. The PowerPoint that you can find here is not exhaustive, but it is like an introduction. So I start using it, and then I will go back to the web page. Okay, so decision theory is a support for decision making, of course. And why decision making is important? Because as we saw today, in some of the cases, we may have different solutions to adapt to climate change. We talked about big dams with respect to distributed water storage, for instance. So it's not an easy decision to decide what is the best solution. Of course, there are economic implications. So we talked about costs today. So, for instance, there was the good question: is it cost convenient, the MOSE, with respect to tolerating once in a while the high water into Venice? Or is it cost convenient to build a big dam, or it's more convenient to rely on distributed small lakes? Decision making is important because in most of the cases we have several different solutions, including the solution of no action, no adaptation. And keep in mind that, unfortunately, we don't have enough resources to adopt all the possible solutions. Sometimes they are also not compatible. And therefore, we need to set priorities. We need to set priorities by considering a lot of implications. I mentioned the economic implication, but it's just one. Then there is, and today we talked about the ecosystems. Ecosystems are extremely important. We talk about commercial activities. There is the public acceptance of it, because we also talked about the visual impact in terms of landscape that is changing. We talked about cultural heritage today. Cultural heritage for Venice, but not only Venice, not only the art cities. There is cultural heritage also in the landscape, in the visual landscape. We know that traditions are important, especially for some countries where the traditions are well established and were founded centuries ago. There are also implications in the public acceptance of the issues like noise, like risk. When we build a huge dam, there is an inherent risk. There is risk also related to any solution. Also, there is risk with no action. But the public acceptance of the risk is, it depends from several issues, several implications that we need to consider. So, and we have different point of views. The engineer has a point of view, which is, of course, subjective. The engineer traditionally relies on hard solutions. Why? Because hard solutions very often have more limited uncertainty. The engineers, usually, they are used to deal with uncertainty, but they are concerned by uncertainty because it implies a responsibility. So the engineer sometimes tends to adopt solutions that are safer, but not necessarily the best ones. And there is the point of view of the citizen, there is the point of view of the politician, there is the point of view of the architecture. They are different. The architects, they are different. And therefore, it is a complicated issue. And sometimes we feel like we don't need a support. We see independently by others or by any support what is the best solution. On the other hand, we have also to be aware that there might be bias, also unconscious bias in our evaluation. And therefore, the tools that help you to take an objective decision are important. And most important nowadays, we need also decision support systems to communicate, to provide support to our decisions. So communication with the public is extremely important. The decision support system may help you to find the convincing support to the solution that you want to promote. So here we come with decision making. Decision making is something that may be boring. Also, the name itself is a bit boring, decision making, like something that is not directly related to climate, to the environment, not directly related to engineering. Actually, like probability and statistics, I think it is a very interesting subject, which has a strict connection with climate, with environment, with our profession. So I am motivated to try to make this discussion interesting, I hope. First of all, we are used to take decisions every day. I mentioned to you several times, and we are used to apply to get support from decision support systems, even if we don't realize it. We look at meteorological forecasting, for instance, it's a decision support system. And we don't realize that we are using a decision support system. But actually, when we decide where to go for the weekend, we look at the meteorological forecasting, and this is an excellent example of a model, a mathematical model, a physical model, a statistical model that is used to support your decision. And there are examples in the history, for instance, the Nilometer, which is shown here. It is a river gauge of the Nile River, and the Egyptians used the Nilometer, so the observation of the Nile River, in order of the water level in the Nile River, in order to decide when to irrigate, when to maybe to harvest also. And this is, again, another example. So, I mean, we are not talking of something that is an abstraction. It is something that we use every day. And of course, the question is how to find the best solution, the best decision support system for our specific problem. Now, decision support systems rely on decision theory. Decision theory has a long history, and it's essentially a mathematical theory. It relies on some statistics, and it is well structured. When, of course, we don't go into the fine details of it. And let me clarify that there are also, and it's part of the decision theory, heuristic approaches that are largely used. Heuristic approaches means that they don't have a structured mathematical basis, but they are based on routinary thinking. They are based on experience. And the heuristic approaches are used in most of the cases in our day-to-day decisions. So you rely on your experience, whether or not to take the car instead of the bus if you have to reach a specific place, but you don't make a mathematical model of it. You just rely on your experience on how long it took to you to drive there with the car, how long it took to you to get there with the bus. And ultimately, you may also rely on your personal preference. Like today, I don't want to take the cars, so even if I know that it takes longer, I take the bus. And this is an example of an heuristic approach, which is not based on a mathematical model, that takes into account also the personal inclination, your personal feeling, your personal thinking that day, which is extremely important when you deal with the public. You have to understand what is the opinion of the public, their thinking, which is something that is not easy to codify mathematically. Sometimes it requires a kind of heuristic approach, something like a narrative. So narratives, you may have heard this term. Narratives are increasingly used in engineering. Narratives are stories that tell us how people may react in a certain condition. And these narratives help you to understand what may be the thinking of people with an heuristic approach. These are also important. And also, the heuristic methods are generally preferred. Why? First of all, for a reason that is not mentioned here, because they are easier. So they are not like a mathematical model that it's, it's difficult for you to understand the concept, and it's difficult for you also to explain to people. Because we have seen today a presentation of a mathematical model. You see that it's not easy. In fact, I said, look at the technical level of your explanation, because if people don't follow you, it's a problem. It's a problem. They may think that you are using a complex word for a simple problem, which means that this is a solution that is often adopted by politicians by like making a case extremely complicated so people don't understand. But people are getting more used to realize that this is a trick. So if you are too technical, maybe a bit of a problem. So heuristic methods sometimes are preferred because they are much easier to explain. Like it's like a narrative. Like if I give too many to people, they don't learn how to be parsimonious. It is something that people understand. It's easy to explain. Or if I feed the dog too much, then the dog may be used to asking more and more food. This is a narrative. It's not based on a mathematical model. Also, heuristic methods are preferred because they are quick, flexible, and they are in a way, as I said, easier to explain. Okay, so let me just say before we make a break that decisional theory evolved significantly in the past 20, 30 years. I wrote here during the 20th century, but actually there have been many and many development that are very recent. I will teach to you some methods that have been proposed 10 years ago, some of them even less than that. So you understand that like hydrology, like climate change, it is a topic that requires a continuous update of the information. Keep it in mind, it's not like designing a building, not like designing a beam where the theory is well established. There are, of course, innovations in any field of engineering, but there are fields where innovation is faster during a specific period. So now decision theory, hydrology, climate change adaptations are fields that are progressing very fast because they are relatively recent. Climate change is a recent concern. So you have to expect that dealing with climate change is a science that is moving faster forward because it just started a few years ago. Okay, let me just look at the last slide, but let me just stop here for now and we take 15 minutes break. Thanks.
And it's
Okay, so one thing, I am getting several requests for additional presentations, so let me make a summary. I have already one booked for next Monday. I'm not sure if I missed other bookings, so I will send an email through Virtuale asking students to confirm to me if they want to deliver a presentation, okay? Because I am not sure if I missed some. For sure, there is one already booked. So this one, you don't need to send me an email, but for the other ones who want to deliver a presentation, please do send me an email to let me know how many people want to make one. As I said, we have room for additional 3. So one is already booked, so we have 2 slots free. I will give, of course, the priority to students, if any, who already booked before, and I may have missed their email. I know that there are for sure at least 3 additional bookings, so there is no room. I'm sorry for everybody. I'm sorry, but I told you that you should have started earlier, and you started too late. And we cannot really make additional presentations unless I convene a specific additional lecture for that, which I don't think it's not the case, because it would be virtual, because we don't have any room, and I'm sure that students may have little interest for an additional lecture. So, to make a summary, I will send an email. Send me an email if you want to deliver a presentation, and please remind me if you already booked it before, so I can look for the original email and give priority to the original booking. And then I will let you know if there is room for another presentation. Otherwise, don't worry, because you know it's not a missed opportunity. I mean, as I said, the exam doesn't change, so you have any way to make your exam in any case. Okay, so decision theory. Let me jump directly to decision theory for water resources management, because decision theory may be applied to several different fields. We are interested in water resources management, so I'm now providing a review of what are the most recent developments, the most recently developed methods, which may be interesting for us. And I am skipping InfoGap for a while with robust optimization, because in water resources management, we are subject to constraints. So we have constraints on the decision that we may take. And one, water resources management, climate change adaptation, one very simple example. If I have to decide if I want to build a dam, I am constrained by the requirement that I have to get enough water from the river to fill the dam. So I cannot say I build a dam of whatever capacity. The capacity is constrained by the available water flow. Because if you build a dam and the dam doesn't fill, you understand you failed. And this is what an engineer doesn't want. Okay, so we have constraints. The constraints are on the design variables, are maybe expressed on the boundary conditions. And in general, these constraints are always present in climate change adaptation. Another very important constraint is money. You have limited resources, so you cannot adopt any solution that you want. You have to check if you have enough resources to build it, to apply it, okay? And another feature of decision-making in climate change adaptation is the presence of uncertainty. We already spoke about it. You know why? We are uncertain about the future climate, so there is uncertainty. And therefore, we are interested in decision theory in the presence of uncertainty and subjected to constraints. This is usually called normative decision theory. Okay. So what are the solutions? First of all, a possible solution may be the robust decision or robust optimization, which means that you identify an optimal solution for a problem, whatever it is, such that the underlying assumptions and constraints are always satisfied in the presence of uncertainty. What does it mean? It means that I may be uncertain about the future climate, okay? The solution that I find is robust, it works under any future climate. There is a minimum performance that is anyway achieved. This means robust, okay? So the constraint, the assumption, and the solution works. It's always satisfied in the presence of uncertainty. And according to this type of approach, the identified solution will always grant the optimal functioning of the system, even in the worst of the several scenarios that can materialize under uncertainty. Okay? Of course, this is conflicting with the purpose of getting the best performance. The best performance may work in ideal condition. In order to identify the best performance, you have to refer to an ideal condition. If you have a set of conditions, of course, the best performance is not the same for all the conditions, which means that if you identify a single best performance for a single future climate scenario, then if the climate scenario becomes different, the solution will not be the best one. So we, in a way, we give up to looking for the best performance for looking for a solution that works with a satisfactory performance under uncertainty. So let's make a difference between a satisfactory performance and the best performance. We look for a satisfactory performance in the presence of uncertainty, and we give up by searching for the best performance. So when we look for optimality, we have to be clear. One thing is optimality with respect to a single scenario, and then we look for the best performance. And another thing is optimality in the presence of uncertainty, which means that you seek a satisfactory performance. The most classical example of robust optimization is given by a problem where a single objective function, so a single target, is to be optimized under uncertain constraints. Okay, a single target. In many cases, we will have more than one target. And then it becomes more complicated. But let's start from the classical problem where I have a single objective function, maybe, for instance, economic cost to be optimized under uncertain constraints. So I look for the less expensive solution under uncertain constraint. Of course, less expensive while still allowing me to achieve the target. Okay, so if the target is I need more water, and I have a solution that is a dam, and another solution is distributed small lakes, I look for the cheaper solution under uncertainty. I want to give you an example of robust optimization. A very simple example is what is called the max-min method, or min-max. What does it mean? It means that you look for a solution with respect to different scenarios, and for any scenario you test what is the benefit, and the benefit is to be computed for any candidate solution. So let's suppose you have 2 scenarios and you have 10 solutions. You refer to scenario 1 and you compute the benefit or the cost, which is the same thing, for any of the 10 solutions. And then you will find a solution that gives the max benefit and a solution that gives the minimum benefit. And then you look at the second scenario, 10 solution, again, max benefit, minimum benefit. So instead of looking for the maximum benefit, you look for the maximum of the minimum, which means that I take the solution that is safer, because I want to avoid the solution that gives to me a very low minimum in case of a certain scenario materializes. So I look for the solution that gives to me the maximum of the minimum benefit. This is called the max-min or min-max method. It doesn't look at the max benefit, but it looks at the max of the minimum, because I want to avoid the minimum of the minimum. You understand? The minimum of the minimum is the worst case. So I want to avoid it. And therefore, I look for the max of the minimum instead of looking for the max of the max. Because the max of the max refers to a single solution and a single scenario. The same solution in the other scenario may give me the minimum of the minimum. So I want to avoid it. This is a very simple example of robust optimization. Of course, it may be something that is too precautionary, because some people may say, okay, maximum of the minimum, but still is a minimum. So let's also consider the opportunity of getting the max of the max, which is an opportunity, which I am missing if I look at the max of the minimum. Maybe that I'm not missing it. Maybe that I can find a solution that is good in both of the targets. So this is robust optimization. And what are the steps that I have to follow? I have to characterize uncertainty with multiple views of the future. Okay, so in case of climate, it's easier. I have several model projections, and therefore I can generate multiple scenarios, and I consider all of them. And then I look at these scenarios without considering their probability, just by looking at the possibility. Because, of course, if I look at the probability, then, with low probability, I may get an unexpected outcome. So let's consider all of them. Like when I talked about the impossible event, I said, it has a low probability. I discussed with you the impossible event, correct? So it means events which have very low probability, but may cause a lot of damage. So let's consider them, even if they have low probability. So even for climate change, let's take all the scenarios and let's look at what happens if each of them is the true one, will be the true one, regardless of their probability, because we have to consider everything, because this is the meaning of robustness. I want to be safe, okay? And I want to be safe even with respect to situations which are extremely unlikely, okay? It's like you drive a car and you consider the possibility of an accident that is very unlikely, but if it is very dangerous, you want to consider it. So basically, with respect to all of these scenarios, I look for the solution that gives to me a kind of safety, even if the outcome is the worst one. Example of the MOSE, they said the MOSE was designed without considering the worst scenarios of sea level rise for the future, and this now is a problem. Maybe they don't materialize, but if the scenario materializes, then it's a problem, even if we have the MOSE. So therefore, if one could go back 20 years, probably it would have been better to conceive something that can be updated, like the question that you raised. Like, okay, can it be updated? Probably not at this stage. Of course, it is easy now to say it would have been better, but 20 years ago, climate change, the perception of climate change was completely different, and the IPCC predictions didn't exist. So it is not easy, because now you have to think of what will happen in 20 years. I mean, such kind of interventions like the MOSE may take 20 years to be done. Like the MOSE, I mean, it took a long time, but it's not easy to make these interventions. So you may be involved in a design of something that will be operational in 2040. Okay, and in 2040 you will have predictions of the future climate that will be different. Maybe they are more precautionary, they are better than those that we have now, maybe that they are worse. And therefore, an innovative vision, a forward-looking vision should be able to elaborate an expectation of how science will evolve. First of all, you have to be fully updated on the most recent discoveries, most recent advances of science, but then you have also to adopt a forward-looking vision. And then you understand that robustness may be something that you prefer, because maybe that, it's not the most convenient solution, but it's robust. And it's an interesting story. Okay, so first of all, let me try to formalize this procedure of robust decision making. Why I am trying to formalize it? Because I understand that this discussion, when I teach these things, they may look like something too much narrative. They may look something like abstract concepts. We are at engineering, and we need as much as possible to try to be rigorous, to give a technical flavor, a technical translation of these narratives. This is extremely important for an engineer, and this is make an engineer different and unique with respect to a social scientist. And unique is not the right word, complementary with respect to a social scientist. This translation from narrative to technical application, it is a very precise task of the engineer, and it is something that is necessary, complementary with respect to the narrative, and is extremely important. I got from one of you in one of the anonymous feedbacks, the ones that, not the one collected by the university, because I don't have access to them up to next fall, but I got, and thank you, because many of you replied to the survey that I set up over Virtuale. I got from one of you a kind of suggestion to try to be more technical, because most of you are engineers, which is indeed very correct. So I want to make an effort on that. So step one, we have to identify the future scenarios, system models and metrics to evaluate success. So future climate scenarios, fine. But we have also to identify the models. Today's presentation, hydrological model, what kind of model? 12 models, fine, because you compare all of them. Or if you want to make water planting and harvesting through groundwater, artificial recharge, this is a topical issue today. We didn't discuss about artificial recharge because it's too specific, but a possibility to store water in the underground, it's a possibility for climate change adaptation. It is not impacting, it is not altering the visual, it's not risky. I mean, it is perfect. So rainwater harvesting, artificial recharge of groundwater, and then we make a groundwater harvesting. But then we have to identify the model to describe the groundwater system. This procedure has the only disadvantage that it's difficult to model, because it's difficult to model the underground. It's much easier to model a river. And so you have to identify also the models. And as I said, in principle, these models, for what is related to climate, reduces to mass balance and energy balance, or let's say energy and momentum balance. Momentum balance, it depends on the applications, but essentially, if you want to reduce to very simple concepts in climate, in modeling the Earth system, is balance equation, conservation equations of mass, first of all, and conservation of energy and the momentum, modeling of flow. So mass allows you to model the storage. Conservation of mass allows you to model the storage. And the conservation of momentum, energy, allows you to model the flows of matter. Okay, and then there might be thermodynamic equation, yes. So conservation of heat, for instance, but it's conservation equation. It's not difficult. Most of them are differential equations. Why? Because you have to discretize the domain. Discretize the domain because these processes are heterogeneous. But then the identification of the specific model is a bit, it depends on the context. And we can't be too specific on that because climate change adaptation is very large. Okay. So if I wanted to be more specific on groundwater, for instance, I can go into the details, but it's too specific, I think, within the vision that we are elaborating here. And then we have to evaluate the metrics, to identify the metrics to evaluate success. It's the cost, it's the economic cost, is preservation of the ecosystem, or in most of the cases will be many of them. And then there is an entire theory that opens, it's opening to our eyes, which is multi-objective optimization. We don't go into the details, just take into account that it looks complicated, but nowadays you have a lot of softwares that allow you to optimize a single objective function, two objective functions, three objective functions, etc. And then you have to identify the solutions. Dam, lakes, groundwater recharge, use of coastal protections rather than beach replenishment. If you have erosion in a beach, one thing may be, one solution is coastal protection, breakwaters, or another solution is beach replenishment. So you bring a sand over the beach, and they have pros and cons. Very often you have to integrate several solutions, because integrating several solutions, you gain in flexibility and you gain in robustness. Because remember, when you seek robustness, then it's very likely that you have to integrate several solutions. And for instance, to give you an example, when we are concerned about the future of water, the first thing that we say is diversify the water sources. Don't rely only on groundwater. Don't rely only on surface water. There has been a drought in Cape Town recently from 2015 to 2014, 2019. And they had severe problems because they had only one water source, which were 3 big dams. So it's only surface water. And when you seek robustness, diversity is an essential ingredient. By the way, diversity is never a problem. So in engineering, keep into account when one speaks about diversity, it looks like it's something ideological. Diversity is never a problem in terms of opinions, in terms of thinking, in terms of solutions, in terms of information. Diversity of information. Some people say, I don't trust satellite, I use only ground observations. Why shouldn't you consider satellites? I mean, integrate both of them. Diversity of information reduces uncertainty. Diversity of thinking. Okay, now step 2, evaluation of system performances. So you have to, for each scenario, you have to check any solution, how it works, and then compute the metrics and etc. And we can term this phase like with the term experimental design. And then you simply evaluate the performances of different alternatives and you estimate the metrics. Good. Step 3, vulnerability assessment. And then you see what is the result of each strategy, and you see the weaknesses of these strategies. And then you may see that there is a strategy that is performing better than others because it gives very good performances in the best case and not so bad performances in the worst case. In this case, in this context, you would be quite happy. But it will happen quite frequently that you see that the best performance is given by the solution that is less robust. The solution may provide very nice performances, very attractive performances if one scenario materializes, and with the second scenario may be the worst one. It happens quite frequently. Because why it happens quite frequently? Because when you see the best when you look for the best performance, usually this performance is achieved in very particular conditions. It's not a best that works best for every condition. Usually you are looking for a singularity. When you look for the average is something that is very frequent. When you look for an extremely good, you look for something that is infrequent. It is unlikely that it happens in all the scenarios. Very often you look for something that is rare. And being rare, it means that in the other conditions, it may be very bad. So it's quite logical. When you look for the best is delicate. It's like a supercar. The supercars, the Formula Ones, are cars that give the best of the performances, but they are not robust. How many failures do you see in a Grand Prix? A lot of them. And sometimes it is just a minor detail that causes the failure, because the super performance is something that is delicate, is not robust usually. While the average car is designed for giving robustness. So what you want from your day-to-day car is robustness, not super performance. Now, then what you have to do next is a scenario discovery. So at this stage, when you have evaluated all the alternatives with respect to all the scenarios, then it's time to bring persons together, to bring people together, and you start by rejecting those possibilities which are not attractive at all. So you will have some solutions that are very bad in some conditions and not so good even in the ideal conditions. So let's reject them. And then you start refining. This is a very, I think, advisable approach. When a decision is difficult and you have several alternatives, keep in mind that deciding among several alternatives is always difficult. It's difficult for you, difficult to communicate. The best solution is start reducing the number by rejecting the solutions that clearly are not good, and people will not complain against that. Because if you reject the best one, of course, some people are complaining. But if you reject the alternatives, if you start rejecting the alternatives which are not so good, then that's perfect. And this is called scenario discovery. Okay. Step 4, adaptation options to address vulnerabilities. Now, you have some alternatives that survived, and you have to identify those options that are more robust. Usually this step is done in consultation with the stakeholders, and you have to try to find the best agreement among them. This is a situation in which you may use a decision support system. So within a robust decision making, within this very general approach, then it may be time to introduce specific approaches, because what I am illustrating now is the general architecture of robust decision making. Then I will give you some more details on specific approaches that can be used in this stage. In this stage, communication is extremely important, and depending on the type of problem and depending on the methods that you know that are available, you may include a decision support system. And what is a decision support system? I will show you later. We will discuss it later. But it is basically something that helps you to compare different solutions in a rigorous manner. In a rigorous, why rigorous? Rigorous because you need to be rigorous to avoid the accusation of subjectivity. You need to be rigorous and transparent. And this is the suggestion of modern decision making. Ensure transparency. Keep in mind that maybe not the best solution. This is an interesting debate. What is the best solution? It is the top-down, where you get, in a way, reassured that something is done, or the bottom-up, transparent, with involvement of stakeholders, democracy, where, you know, of course, we see the advantage, but it may imply that you don't reach a final decision, and you may generate absence of solution. This happens quite frequently when dealing with climate change. When dealing with climate change, everybody complains about it, but if you look at the solution that we were able to adopt, it's not, we can't say that we are happy at the global level and also at the local level. So it's an interesting debate whether or not we should force a top-down. I think that today there is a clear indication to avoid top-down and to prefer a bottom-up approach. On the other hand, it's not easy. It's not easy, and you can see what are the limits of this approach. In the nobody's happy. In the everyday routine, you see that for some important decisions, nobody's happy, and the decisions that are taken are not really satisfactory, are not the optimal one. Anyway, there is a clear indication to which I clearly support, which is try to use a bottom-up approach, try to be diverse, transparent, and rigorous at the same time. Okay, now let's try to go into the details of these decision support systems. So the question here is, let me go back with the slide. The question is, step 5, decision makers and stakeholders can bring in their assumption regarding the likelihood of the future scenarios and discussion with the stakeholders. And let me go back to this InfoGap decision method. This is an example. I think it is extremely interesting in the context of climate change. This method is widely used in the context of climate change, not particularly in water resources management. So it's not really my field, but I think I wanted to bring it up front in my teaching, because I think it's a very interesting example precisely in the climate change context. Keep in mind that water resources, the science of water resources has a long history in decision making, optimization decision making. So it is indeed a leading science in that respect. But clearly now it has been extended also, this necessity, to any issue related to climate change. So InfoGap was proposed in 2001, so it's very recent. It has been applied not many times to assist decision making, in particular when there is uncertainty. And also InfoGap has been conceived to work with imprecise uncertainty. So information on uncertainty is not really so reliable, which is the case for climate change. In most of the cases in climate change, we know that the information is uncertain. Think at the future climatic scenarios, it's uncertain. But how much? It's a problem. It's still a problem. We have several projections, but we can't associate to each of them a probability. There are attempts to do that, but actually they are not very rigorous probabilities. And therefore, InfoGap, it has been conceived in this way, and to overcome this problem. And in fact, what InfoGap does, it's not to find the best solution under uncertainty, or the most advisable, the most robust solution, let me say, under uncertainty. InfoGap reverses the reasoning. It investigates what is the max level of uncertainty, or the level of uncertainty, let me say, that allows me to take a robust decision. So it reverses the question. It's okay. I want to seek a robust decision. What is the level of uncertainty that I can tolerate? If this level of uncertainty is very large, perfect, I am happy. If the level of uncertainty is very small, I am not happy. Independently of my knowledge of uncertainty, I'm just trying to see, I'm reverting the approach in order to see what is the max or the optimal, let me say, uncertainty that I can tolerate. I am reluctant to say the max, because you will see that in some cases we will look for the maximum uncertainty tolerable, and in some cases we will look for the minimum uncertainty tolerable. And I will explain you why. I think the approach is interesting, because if you think of something that you don't know the cost, for instance, because like it is very frequent in climate change adaptation, you have seen the estimate of the cost of the MOSE has been increasing exponentially, because at the beginning, it is always the case that we get an estimate of the cost that is not precautionary. It's much lower than the actual cost. So in a case like this, reverting the decision means, let me see what is, let me identify what is the max level of uncertainty of the cost that I can tolerate. Instead of estimating a cost under uncertainty, let me try to assess what is the maximum level of uncertainty in the cost that I can tolerate. So if the estimated cost is 1 billion, what is the maximum level of uncertainty that I can tolerate in this estimate? So it may be quite large, because maybe that if the cost increases, you are able to find additional support. So in this case, you are happy. If you see that even a small underestimation can cause a problem, then it's a concern. And we will look into the detail of this method next Monday. I think for now we can close here. Do you have any question?
Prof, can you hear me?
Yeah, yes, please.
Okay. Can you explain briefly what is the max of the minimum benefit?
Okay. Yeah, I didn't go into the detail, and let me think how I can. So let me try to explain by words. So we are in the presence of several different future scenarios and several alternatives. So you can estimate the benefit given by each alternative for each scenario. And then each alternative will give you a max and a min for each in general. Overall, the scenarios, you will find for each alternative a maximum benefit and a minimum benefit. So for instance, if I want to build a dam and I want to estimate the economic cost, the alternative is the dam. I have 10 different future scenarios. I estimate the benefit of the dam for each of them, and I can identify a maximum and a minimum. The same applies for another solution. And therefore, I may decide to look for the solution that gives to me, for all the scenarios, the best benefit. And then I identify the DAM, for instance, which, in case I get scenario 1, gives to me the maximum benefit. But if I look at the other scenarios, I will have benefits that are lower, and I can identify a minimum for the DAM. And maybe that this minimum is very low. Perfect. Let's consider a second solution, small lakes. Again, maximum and minimum benefit. In this case as well, I can identify the max over all the scenario and the minimum over all the scenario. If you have other solutions, same thing. Now, at the end of the story, you can decide for the solution that gives the possible max, the max of the max, which means that you don't care about the minimum. So if you adopt the solution DAM, because it gives the maximum benefit over all the solutions, you don't consider the minimum. What is the minimum benefit that you may take for a DAM? You don't care. Another criteria may be that you look at the minimum of the DAM, the minimum of the lakes, and the minimum of any other solution, and you select the solution that gives to you the maximum of the minimum. Why? Because you want to avoid the minimum of the minimum. It's a different choice. It's a different solution. I'm not sure if I was clear. Was I clear or not? Was I clear or not?
Okay, maybe I have to think about it a bit more,
Okay,
but
if it's not clear, I can send an email with a sketch. Okay, it's with a sketch is very easy. I don't think I can make the sketch now on the blackboard because I need to think of it. But if it's not clear, send an email. I may send a sketch by email. Okay, other questions? Okay, thanks a lot. Let's meet next Thursday. Those of you who subscribe to the field trip, you know where we have to meet. One thing that I didn't tell you, and if you have any problem, send me an email. I will be connected and I will check my email, okay? So let's communicate in this way if you have any problem, okay? And another thing, some of you asked me today, can I still subscribe? Yes, but by today, please. So if you want to subscribe, send an email by today, okay? There are still places. Thanks, and see you Thursday or Monday.
bye, thank you.
Bye-bye.